Okay, so this is Chapter 5 now. We'll call this Lecture 5, Part 1. And in this chapter we will talk about another important topic in calculus called integrals or integration. So Lecture 5, Part 1, integrals. All right, so here we go. So in Chapter 2, we used the tangent and velocity problems to introduce the derivative, which was a key component of differential calculus. Now we're going to be talking about integral calculus. So in much the same way, this chapter starts with the area and distance problems and uses them to formulate the idea of the definite integral, right? So we can use the definite integral to calculate volumes of objects, lengths of curves, population predictions, forces on a dam, work, economics, and so forth. So to do integrals properly, we have to connect them to what we know already, and we've done quite a bit with differential calculus. So there's this fundamental theorem of calculus which relates differential calculus to integral calculus, and we'll go over the proof of that. So the first topic, areas and distances. Okay, we're going to be dealing with limit problems again. We're going to use limits now to calculate the areas under curves, special types of curves, and as well as distance problems. So find the area of a region S that lies under the curve y equals f of x from x equals a to x equals b. Right, and that's shown in this figure right here. So here we have the red curve is some hypothetical function y equals f of x, and so the orange zone is the area we're trying to find. So x ranges from a to b, and we want to find the area bounded on the left by x equals a, on the right by x equals b, on the top by y equals f of x, and on the bottom by the x-axis. X goes from a to b. So what is the area of this curve? Right. This caveat is that f of x is a continuous function. It's greater than or equal to 0, and so forth. Okay. All right. So what does the word area mean? So we need to set some ground rules as to what we consider to be the area. So for instance, a rectangle, the area is defined as the length times the width. All right. So that would be a good reference understanding for the area of an object. For triangles, of course, the area is 1/2 the base times the height. And for polygons, okay, how do you calculate the area of this particular polygon? And the proposal is, okay, well, why don't we split the polygon into 4 triangular type regions and then sum up the areas of each of the triangles, and the cumulative sum would be the area of the polygon. Okay. But it oftentimes isn't easy to find the area of a region with curved sides. Right? So if you have a curvilinear figure, such as like a quadratic, it's oftentimes not very easy. So how do you inscribe rectangles or so forth under the curve and sum up those areas? So that poses challenges for this so-called area problem. So in defining a tangent, we approximated the slope of the tangent line by slopes with secant lines, and then we took a limit of these approximations. So we're going to do the same thing with areas. We're going to approximate the area under a curve through by summing up the areas of smaller and smaller rectangles that are inscribed under the area of under the curve. So let me show you a picture. So we approximate the region S by rectangles and then take the limit of the areas of these rectangles as we increase the number of the rectangles. Right, so for example, let me explain what I mean. So here we have y equals x squared, okay, the base parabola, and we want to find the area under y equals x squared between x equals 0 and x equals 1. In other words, this shaded region S. Okay, and this, of course, it's bounded below by the x-axis. All right, so the way we would calculate such an area. Okay, so we first notice that the area S must be somewhere between 0 and 1. Yeah, okay, so so maybe we should stage a lower and upper bound for the areas. If we were to say draw a unit square set like this, okay, we know that the area under the y equals x squared, the area of the orange region, is going to be less than 1 square unit, which is right here, marked in blue. And it's going to be greater than 0. So we know it's going to be somewhere between those two numbers. Okay, so that should be obvious. But we can do better than 1, right? We can. If we were to take the area S and divide it into 4 strips, S1, S2, S3, S4, as shown in this figure. And so if we draw vertical lines from x squared to the x-axis, and we have quarter length intervals, each interval length is the same width, okay, so we would have 1/4, 1/2, 3/4, and 1. Then we could say, okay, we could calculate the areas of S1, S2, S3, S4, add them up, and we'll get the area of S. Okay, but what are those areas? Okay, so we can approximate each strip by a rectangle whose base is the same as the strip and whose height is the same as the right edge of the strip. So in other words, what this article is saying is, okay, so we take 0 to 1, split it into 4 equal length segments like this, okay, and then say at 1/4, you come up and you evaluate the function y equals x squared at x equals 1/4. And that will determine the height of, say, this particular rectangle. And so now you can calculate the area of this rectangle. So that would be 1/4 would be its width, and then its height would be 1/4 squared. Because we know that f of x is equal to x squared, right? And the height of the rectangle is where we plug in the value of x, and then f of x determines the height of the rectangle, okay? And so we just sum up the areas of these 4 approximating rectangles, and we'll get a better solution to the area under the curve. It's not the best solution, but it is a better solution. Okay, like so. All right, so the area of this first rectangle right here, this one would be what? 1/4 times 1/16, so that would be 1/64 square units. Okay. All right, so that's the area problem. This is known as the area problem for integral calculus. Okay, so the heights of these rectangles are the values of the function f of x equals x squared at the right endpoints of the subintervals. Yeah, so emphasis is right endpoints. So you take the interval along the x-axis, and at the right endpoint of the interval, you plug it into the function, and you get the height of the rectangle. So these are the heights of the rectangles are based on the substitution of the right endpoints of the intervals on the x-axis into the function. Okay. So each rectangle has width 1, and the heights are 1/4 squared, 1/2 squared, 3/4 squared, and 1 squared. You can see the heights of the rectangles. So you just sum up the areas of these 4 rectangles, and you'll have an approximate area under the curve. Okay, and we let R4 be the sum of the areas of those approximating rectangles. And R, of course, stands for right endpoint. Okay, so R4, summing up, okay, is 0.46875. So that would be, or 15/30 seconds, that would be what you would consider to be the area under the curve. This would be the R4 sum, the right 4 sum. R means right, 4 means rectangles, each of which have equal width. All right, so the exact area S will be less than R4. So you can say 0.46875 is considered to be an upper bound for the area under the curve, under y equals x squared from 0 to 1. Okay, now instead of using the rectangles in this figure, we could use smaller rectangles, okay? So in this case, they chose to use smaller rectangles. So we could have a lower bound for the approximate area. Here the heights are the values of f at the left endpoints of the subintervals. In other words, what they did here was, okay, so they took the 4 subintervals like so, and then the heights were calculated at the left endpoints of the rectangles, okay? So take this second interval, and then the height of this rectangle would be evaluated at the left endpoint of the interval on the x-axis. So you would plug in 1/4 into x squared to get the height of the second rectangle. The height of the first rectangle, of course, is 0. The height of the second would be 1/4 squared. The height of the third would be 1/2 squared, and the height of the fourth rectangle would be 3/4 squared. Okay. So the leftmost rectangle has collapsed because its height is 0. Okay, so just a little informational piece there. All right. Okay. So we have what's called the left four-sum. L meaning left, 4 meaning rectangles. So L means that the heights of the rectangles are determined by the left endpoints of those rectangles. And so when you add up the L4, the areas of the 4 rectangles based on the left endpoints determining the heights of the rectangles, you get 7/32 or 0.21875. And so this will comprise a lower bound for the area under the curve, right? So the true area is between 0.21875 and 0.46875. Not too bad for the true area, but eventually we want the exact area, okay? So we can repeat this procedure for a larger number of strips. All right, so if we increase, say, using left endpoints, we have how many strips now? 1, 2, 3, 4, 5, 6, 7. 7 strips here, right? Well, actually 8. They're using 8 strips. So they divided the interval into 8 subintervals. And if you notice that as we increase the number of strips, these little excess areas for the L4 sum, you see these excess areas? They became smaller. The excess became smaller. Compare the area of this excess with the L4 sum with the areas of the L8 sum, and you notice it became smaller. And the overshoot areas right here, these excess areas, they also became smaller. Okay? They became smaller as the number of rectangles increased. Okay, so, and we can make a table and compare the errors as we increase the number of rectangles. Okay. So the L8 sum turned out to be 0.273, whatever, and the R8 sum turned out to be 0.398. So we actually got an improvement in the preciseness of the actual area. In other words, the range became smaller. Okay, and so it looks like kind of like a squeeze theorem. Squeezing action is taking place here. The left sum is approaching the right sum. Okay, so the true area of S lies somewhere between 0.273 and 0.398. Okay, and we can still go better by increasing the number of strips. Okay, and so so here we have a table. The table shows that the results of similar calculations using n rectangles, whose heights are found with left endpoints or right endpoints. Okay, so for instance, n right here in this table represents the number of rectangles that we used, whose areas we sum up to calculate the area under the curve. So if n equals 10, the left sum is this, the right sum is this. And now notice the pattern as n increases. Look at the left sum. If you notice the trending of the numbers, they seem to be converging toward 0.3328. And if you look at the trending of the numbers for the right sum, they seem to be converging toward 0.3338 as well. So it looks like the left sum and the right sum are turning into the same number as n grows larger and larger. And that's because those excesses are becoming smaller and smaller. Right? So you could probably infer from this table that as n grows very, very large, L and R will converge to, say, a third. Okay? So with 50 strips, with 1,000 strips, you see such. And this is probably done by a computer. And so a good estimate is obtained by averaging the numbers. Okay, so you can average the two numbers and you get at n equals 1,000, so the average is 0.333. Okay, that's not bad. And from the values in the table, it looks as if Rn is approaching a third as n increases. Okay, and so the limit as n approaches infinity of the right sum is a third. Okay, so you can pretty much consider that to be the area under the curve. And Rn is the sum of the areas of n rectangles. Each rectangle has width 1 over n, and the heights are the values of the function f of x equals x squared at the points 1 over n, 2 over n, 3 over n, n over n. And this is the heights, that is the heights of each of the rectangles shown in this figure would be 1 over n squared, 2 over n squared, 3 over n quantity squared, n over n quantity squared. Okay, so you can see all the areas of the rectangles. So we sum up each of the areas of these rectangles to get the area under the red curve. Okay, so that's the geometric argument. All right, so R sub n, okay. So R sub n is 1 over n. This would be, okay, so this would be the width of a rectangle. Yeah. Now bear in mind n is some positive integer. This would be the height. Okay, this would be the width of the second rectangle, height of the second rectangle, width of the third, height of the third rectangle, width of the nth rectangle, height of the nth rectangle. Okay, and then so when we add up all these numbers, well, we can factor out 1 over n and 1 over n squared, and we'll have 1 over n cubed times the sum of the squares of the first n integers. Okay, so this would be the right sum formula. Okay, that's the right sum formula, represented as a series. All right, interesting. So we need to find a formula for the sum of the squares of the first n positive integers. And it turns out that the sum of the squares of the first n integers is this closed form solution, n times n plus 1 times 2n plus 1 over 6. And I'll leave it, you can verify that. Just plug in some number, say 5, add up the sum of the squares of the first 5 integers, and then plug 5 into this formula, and they'll be the same thing. Appendix E of your text, example 5, shows the proof. The proof is done by induction, and I'll assume that this is probably your experience from algebra or other math classes. I'm not going to have time to go through the proof by induction, but we'll make use of this formula right here. So this formula should be available to you. You'll probably need to use this for WebAssign questions and possible test questions as well. I'll assume that you'll understand what this means. It's just an algebraic equation. All right. Okay, so if we substitute in that sum with the closed form solution, which is this. Okay, this is called the closed form expression for the sum. We now have a formula for R sub n, which is 1 over n cubed times this closed form sum. And then after simplifying it algebraically, this will be your R sub n. Okay. All right. Now the next step, of course, is what happens is n approaches infinity. Now, when n approaches infinity, the Rn sum will equal to S, the true area. So we'll take the limit as n approaches infinity for this expression. And we can probably use something like L'Hopital's rule or perhaps something. We'll see. All right. So Rn, the limit as n approaches infinity of R sub n. Okay. They're going to use the limit laws here. Would be the limit as n approaches infinity of the expression. They factored it into 3 products. And then they used, then they did the division of each of the products in n, and then they used the theorem that the limit as n approaches infinity of 1 over n, of course, is just 0, and so you get 1/3. So that's your true area. That is the true area under the curve. All right, so that's how it's done. And you can do the same exercise with the limit as n approaches infinity of L to n. It'll be the same result. All right, so from the figure, it appears that as n increases, Rn becomes a better and better approximation to S. You can see as you densify the number of rectangles, you almost end up with a solid fill under the curve. The excesses go away. They vanish as n becomes really, really large. Same for L to n. That's what's shown here. So the area, again, is equal to the limit as n approaches infinity of Rn, which equals to the limit as n approaches infinity of the left sum, which is equal to R, which is equal to 1/3. Okay, so now we can generalize this to a more a hypothetical function y equals f of x. So let's proceed to generalize the concept. So start by subdividing the area under the curve S into n strips, like so. S1, S2, and S1, S2 up to Sn. Each of the width of these rectangles, or the strips that is, they're not rectangles yet. The width of each of the strips are equal. Okay. So notice the subscripting. The width of each interval is the width of the interval A to B. Okay, so from A to B is B minus A, so that's the interval on the x-axis, and its width is B minus A. And so the width of each of the n strips we call delta x, okay, which will be the width of the entire interval divided by the number of subdivisions of the interval. All right, so that's pretty intuitive. And these strips divide the interval from A to B into n subintervals. Okay, so x of 0 is equal to A and x of n is equal to B. So these are the widths of each of your intervals. Okay, or these are the intervals actually. These are the intervals which really constitute the width of rectangles. Okay, or the endpoints of the rectangles. Okay, so these will be the bases of each of the rectangles, and the width of each of these subintervals is the same, namely n. All right. This is, by the way, it's called a partition. The partition of the interval. All right. So the right endpoints of the subintervals are, well, x of 1 is equal to a plus delta x. All right. So for instance, it goes like this. Here's a. Okay. There's a, and here's x of 1. Here's x of 0. Okay? This is delta x. Okay? Now here is x of 2. All right? Now the distance from x of 1 to x of 2 is delta x as well. That's delta x. Okay? So to get to x of 2, you start at a. Okay? To get to x of 2 from a, you start at a, and then you add 2 delta x's. Okay? And that puts you at x of 2. So again, here's x of 3. Okay? That's delta x from x of 2 right there. So to get to x of 3 from a, you have to add 1, 2, 3 delta x's, and so forth. All right, so that's what this means. All right, for your partition. Okay. All right. So let's approximate the ith strip S of I by a rectangle of width delta x and height f x of I, which is the value of f at the right endpoint. So the ith strip, it's kind of hard to see here maybe, would be, okay, here's the ith strip right here. Okay, so there's your ith strip. Okay, so its width is delta x, okay, and its height is based on the right endpoint. So you take x of I, plug it into f of x to get the height. And so f x of I, delta x, is the area of the ith rectangle, right? Because it's x of I is somewhere in the partition of A to B. Okay. Now notice if we use the right endpoints of the intervals to calculate the areas of the rectangles don't often overshoot the curve, like in this case. Okay, so if you have like a decreasing curve situation, well, the right endpoint could undershoot the curve and such. So you could have a situation where some of the rectangles will be below the curve, some will stick out above the curve, some will stick out above and below the curve, like this one. This one could be above in some parts of the interval and below in other parts. So it all hinges on what the right endpoint is. Okay, so don't be tripped up by that notion. Okay. So we may think of intuitively as the area of S is approximated by the sum of the rectangles, some of these rectangles. So R sub n is equal to fx of 1 times delta x plus fx2 delta x all the way up to fxn delta x. All right. So the right sum would be the sum of the areas of these rectangles. Okay. Remember, we're generalizing the first example. So for n equals 2, shown here for n equals 2, n equals 4, 8, and 12, you can see they're calculating the areas of those rectangles, the sum of the areas of those rectangles. And so as we densify, as the number of rectangles increases, you see that these excess areas, as shown, grow smaller and smaller until they vanish. So we define the area A of the region S as follows. Okay, the area A of the region S that lies under the graph of a continuous function f is the limit of the sum of the areas of the approximating rectangles. Okay, so in other words, area is equal to the limit as n approaches infinity of the right rectangle. All right, and so what is R sub n? Okay, so this is the area of the first rectangle, the area of the second rectangle, and the area of the nth rectangle. And so if we take the limit as n approaches infinity, well, it will add up an infinite number of rectangles, and that will be your area. Now this is a definition. Okay, so this is what we define to be the area under any curve, so long as the function is a continuous function. And later on we'll have a case where it doesn't necessarily have to be continuous. Okay. Yeah, so the limit exists because f is continuous. Okay, you can also use the left limit if you wish. Okay, so the distinction is, okay, if you look at the right limit of course will start at x1, but the left limit will start at x sub naught. Okay, so notice the subscripting, there's a slight variation in the subscripting. The left limit is evaluated from x naught to xn minus 1, whereas the right limit went from x1 to x sub n. Okay, which makes sense because you start at the right endpoints for the right sum, and you start at the left endpoints for the left sum. Okay, so these are definitions for the precise area, so you just have to take an infinite limit, do essentially what we did in Chapter 2. So it now becomes a Chapter 2 type problem. Okay, now we talk about sample points. Okay, so instead of using left endpoints or right endpoints, we could take the height of the ith rectangle to be the value of s at any number, x of I star, in the ith subinterval. So we don't have, what this is saying is we don't have to use the endpoints along the width of a strip. We could select any points, including the endpoints within the strip, and we call these numbers x of I star sample points. So in other words, we could choose the midpoint of the interval, or we could choose a random point in the interval, and we can mix the modes. We can choose a midpoint in one interval and the right endpoint in another interval. Okay, we can choose the heights of the rectangles based on any value we desire. Yeah, so in this case, the sample points for this figure are random, looks to be random. Here it's kind of close to the left endpoint. Here it looks like the midpoint, kind of close to the right endpoint. So they chose to choose the heights of the rectangles based on just some random selection. Nevertheless, the result will still be the same. All right, so the generalized expression for the area of S is the limit as n approaches infinity of the function evaluated at a sample point on each of the intervals. Okay, remember delta x still remains the same. It's your partition, but the x of i's, of course, are not all the same. So this x of I, just some selection on the first interval. X of 2 star is some selection on the second interval, and so forth. Okay, there's no prescribed way of selecting the arguments to the function, as long as that there's some value within the appropriate delta x. Okay. Sigma notation. Okay, so we introduced sigma notation. Okay, so instead of writing out an expression like this, okay, which is somewhat lengthy, we use this notation sigma. And sigma stands for, you take this number right here, or you take this function. What sigma notation means is it's a sum operator. It's called a sum operator. You take this expression right here, okay, and you basically start off with index, I is called the index, and you start off with index equals 1, and you plug it in to the index to the subscripts here. So for instance, you take I equals 1 and you plug it 1 into the subscript. So you'll have x1, f of x1 times delta x, okay? Then you go and you add 1 to 1, so you get 2, okay? So if I equals 2, and then you check, is 2 less than n? And if 2 is less than n, then you'll add to this number, you'll plug 2 into the subscript, okay? All right, and then you increment 2 by 1, okay? So 3 is next. And you check, is 3 less than n? If so, then you'll plug 3 into the subscript, okay? And you'll add that result to the existing sum, to the running total so far. So this is a compact way of writing sums, okay? It's a shorthand notation. It's called the sigma notation, the summation notation. All right, so that's the definition of a summation. All right. So now we have, okay, so this would be the right sum. Okay, so this first expression is the right sum expressed using sigma notation. The second term would be, of course, the left sum expressed using sigma notation. See, if you take I equals 1 and you plug it in to the subscript, you'll have x of 1 minus 1, which is 0. So we're actually doing subscript arithmetic now. So this would be fx naught. So this would be your left sum. And then this would be your random sample, your sample point sum, okay? So we have all of these expressions. And of course, we want, for a continuous function, we want all three of these quantities to be the same in the limits. Okay. All right. So, for instance, the sum of the squares of the first n integers we've shown is equal to this. And the proof, of course, is in Appendix E, proof by induction. Right. And that A be the area of the region that lies under the graph f of x equals e to the minus x between 0 and 2. Using right endpoints, find an expression for A as a limit. Do not evaluate the limit. And then estimate the area by taking the sample points to be midpoints and using 4 subintervals and then 10 subintervals. Okay. Now, so before we proceed with this example, I'll show you another thing that might pop up in WebAssign. Now, WebAssign will ask you to find R sub n, okay? And it'll ask you to find L sub n. There's another parameter called M sub n. That's just called the midpoint sum. And that, of course, is just done by, instead of using the right endpoints or the left endpoints, you'll use the midpoints of the interval to calculate the heights of the rectangles. So I'll assume that you know how to find the midpoint of an interval. You just take the left endpoint plus the right endpoint and divide it by 2, and that will be your midpoint. And using that point, you'll find the height of the rectangle. Okay, so it's pretty straightforward. All right, so let's see. E to the minus x. We want to find the area under the curve from e to the minus x from 0 to 2. All right, so let's see if we can do that. All right, so A is equal to 0, B is equal to 2. So the width of the subinterval will be B minus A over n. Okay, so that's 2 over n. So x of 1 is 2 over n, x of 2 is 4 over n, x of 3. Okay, so convince yourself that that will be the case. So A is 0, B is 2, okay? And so we partition this interval along the x-axis into n subintervals, okay? And so we have n partitions, n subintervals, and then so this would be your x of 1 right here. This would be your x of naught, okay? And so you take 2, so the width of this interval would be the entire width divided by the number of partitions. So this would be 2 sub n. Okay. So and then so if this is 2 sub n, then this would have to be, so this x of 2 right here would be twice of 2n, right? 2 sub n plus 2 over n, that's 4 over n. And then this x of 3 would be 3 times 2 over n, which would be 6 over n. And then x of I, okay, x of I well, that would just be I times 2 over n. And then finally, x of n, here's your x of n, which is equal to b. That would just be 2 over n times n. Okay, so that's your partition. Those are the widths of it. These would constitute the right endpoints of each of the intervals, or n intervals. Okay, all right. So there's your delta x. So your r sub n, okay, fx1 delta x, fx2 delta x, all the way up to fxn delta x. And now we just replace f of x with its definition. So that would be e to the minus x1 times delta x, e to the minus x2 delta x, and so forth. Now, and then you replace x1 with what we said it was. It's x sub 1 is, happens at 2 over n. X sub 2 happens at 4 over n. Right? Just replace x sub 2 with its definition in n, and then x sub n happens at 2n over n. All right, so now we have a function in terms r sub n in terms of n alone. Okay, let's see how that works. All right. Okay. So area is equal to the limit as n approaches infinity of Rn. So now factoring. So if we were to factor out 2 over n, okay, we can factor out 2 over n and then use the properties of the exponential function. Well, we factored out a 2 over n and we have this sum right here. Okay, so the limit as n approaches infinity. So now what we do is we take this expression and we use sigma notation. Okay, so convince yourself that this would be the sigma notation. So if we plug in 1, we'll have e to the negative 2 over n. If we plug in 2, we'll have e to the negative 4 over n. If we plug in 3, e to the negative 6 over n. If we plug in n, we'll have e to the negative 2n over n. So you consolidate this sum expansion into using sigma notation. And then you can write a concise area is equal to the limit as n approaches infinity for this expression. Okay. So that's the area under the curve. So where is e to the minus x? It goes like this, right? Okay, and so you want to find the area. Basically, so this is e to the minus x. And so you're trying to find, you're trying to find this area right here. Okay, so to keep it in perspective, that's the area you're trying to find. Okay. Okay. So with n equals 4, the subintervals of equal width. Okay, so delta x is 0.5. Okay, so how is delta x 0.5? Well, you go b minus a over n is delta x. Okay, and so n is 4, b is 2, a is 0. And so here your interval, here's your partition, the endpoints of the subintervals. And then you take the midpoints. Okay, so first interval, the midpoint is 0.25. Second interval, the midpoint is 0.75. Third interval, the midpoint is 1.25. And the fourth interval, the midpoint is 1.75. So those will be your sample points. These will be used to determine the heights of your rectangles. And this, of course, your delta x, the width of each of the rectangles is 0.5. So now we can calculate the M4. So that's what we're after now is M4. This is the M4 sum, the midpoint 4 sum. Okay, and so here's y equals e to the x, calculating the M4 sum. Okay, so it would be the sum from I equals 1 to 4, n is equal to 4. F evaluated at the sample point on the ith interval times the width, which is 0.5. And so they plug in the numbers. This is called the sum expansion. Delta x is 0.5. F of whatever x sub I is. Summing up the areas, we get an approximate area of 0.8557 square units. Okay, all right, so that's the area under that curve. Okay. So with n equals 10, okay, You'll recalculate your midpoints because the width of the intervals along the x-axis becomes smaller, right? And so with 10 rectangles, the height's determined by the midpoints. Your delta x is 0.2, you get a 0.8632. This is called a refinement of the partition. The denser and denser you make your partition, it's called a refinement. Okay, so of course n equals 10 will be a better estimate than with n equals 4, right? So let's consider a distance problem. Find the distance traveled by an object during a certain time period if the velocity of the object is known at all times. Okay. If the velocity remains constant, then the distance problem is easy to solve. Distance is equal to velocity times time. But if you have a varying velocity, if the velocity varies, it's not so easy to find the distance traveled. Okay. Suppose the odometer on our car is broken and we want to estimate the distance driven over a 30-second time interval. Okay, so take speedometer readings every 5 seconds and record them in the table. So time equals 0, velocity is 17, time equals 5, velocity is 21, 10 seconds into it, 24 miles per hour, and so forth. So you can see the table, and so we want to calculate the distance traveled. Right, so how do we do that with time and velocity measurements? So in order to have the time and the velocity in consistent units, they convert the readings to feet per second. Okay, so yeah, because the velocity is in miles per hour and the time is measured in seconds. So convert all of these rates into feet per second. Okay, so during the, we take the velocity during the time interval to be the initial velocity. Then we attain, okay, so the velocity during that time interval, what's going on here? Okay. During the first 5 seconds, the velocity doesn't change much, okay? So we estimate the distance traveled during that by assuming the velocity is a constant, okay, during the first 5 seconds. All right, so if we take the velocity during that time interval to be the initial velocity, 25 feet per second, then we obtain the approximate distance traveled to be 125 feet. Okay, so they converted miles per hour to 25 feet per second. And then they just said it's approximately constant. Okay. During the second time interval, the velocity is approximately constant, and we take the velocity then when t equals 5 seconds. Okay, so they're using the right endpoint. The right endpoint for the velocity measurements. Okay. Okay. So here's their calculation. So they say it's 1,135 feet would be the distance traveled. So you just take the right endpoints of the table, and then you sample your rates. You calculate the rates at each of the right endpoints, and then sum them up. Sum up the total distances. Oh, okay, so actually you could have used the left endpoints or the right endpoints. So that's all they're saying here. It's just a left endpoint, right endpoint problem. Okay, every second, of course. You could sample more frequently, which it does. Okay, so I'll let you read through this. So, yeah, so here they sketch a graph of the velocity function of the car and draw rectangles whose heights are the initial velocities for each time interval. Okay, so they're using the left sums here, the left endpoints. So here's your velocity profile. Okay, and then they use the time at 0, the times at 0, 5, 10, 15, 20, 25 seconds, and then they sample the velocity at each of those times in feet per second, and then they just sum up those areas, okay, to get the distance traveled. So the areas are the distance traveled. The area of the first rectangle, of course, is 25 by 5, which is also our estimate for the distance traveled in the first 5 seconds. So area of each rectangle can be interpreted as a distance because the height represents the velocity and the width represents the time. Okay, height is velocity. Width represents the time. The height is determined by the left endpoint of the time interval. Okay. So the L6 is 1135. So suppose an object moves with velocity v is equal to f of t, where t is between a and b, and f of t is greater than 0. So the object always moves in a positive direction. Okay. Take the velocity readings at times t0 equals a, t1, t2, tn equals b, so that the velocity is approximately constant on each subinterval. If these times are equally spaced, then the time between the consecutive readings, of course, is b minus a over n. That's your delta t. During the first time interval, the velocity is approximately f of t naught, the left endpoint. So the distance traveled is f of t naught times delta t. That's your area of your rectangle. And the distance traveled during the second time interval is ft1 times delta t. And so the total distance traveled would be this formula, the summation formula, which you can collapse into a sigma notation. I minus 1 would be your subscript. This would be the left endpoint sum, the L sum. Okay, you could also have used the right endpoint sum. The more frequently we measure the velocity, the more accurate our estimates become, and that's what your speedometer does. And so it's plausible that the exact distance traveled would be the limit of the left sum, which is equal to the limit of the right sum. Okay, so we'll prove that in section 5, part 4. Okay, summary, sorry. Okay, so that would be it for section 5.1, an introduction to integral calculus. We actually didn't use integrals, we used sums. Okay, we'll introduce the integrals probably in the next section. So get started on your web assigned for chapter 5. This will be section 5.1 conclusion.